Hello to all of you and welcome back to my SP2 channel. So we're going to be looking at bond polarity for this lesson. I've got polar, non-polar, covalent bonds. I've got a little bit on the electronegativity and how we can use that to understand the polarity of the bonds. I should talk about dipole moments, and I also have a practice for you at the end. Okay, so starting by the definition of polar and non-polar covalent bonding. So for the polar bonds, we are going to have uneven sharing of electrons between the two atoms that are making the bond. And here is an example for you, hydrogen chloride. So what I have here is I have chlorine that is having a stronger pole on the shared electrons and drawing them closer to itself. And therefore, that is going to be our polar bond. For the non-polar covalent bonding, we're going to have equal sharing of electrons between the two atoms, which means that they have equal pole on the shared electrons. For example, if I have something like hydrogen, right, H2, both hydrogen's atoms exert the same force on the shared electrons, and therefore we're going to have equal sharing of them, giving us a non-polar bond. Okay? Okay, so the force that I have, like a stronger, weaker force, can be understood by looking at the electronegativity, right? So the electronegativity here is helping us determining whether a bond is nonpolar, polar, or even ionic. It defines an atom's ability to attract electrons within a molecule. If I have higher electronegativity, it means that the atom attracts the electron more strongly toward itself, right? And the electronegativity is related to ionization energy and the electron affinity, right? If I have high values of, electronegativity, I know that I'm going to have, a stronger affinity, and I'm expecting to have high values for the ionization energy. Now, a quick reminder from our periodic trends, right? We mentioned that for the electronegativity, it is always increasing across a period, moving from left to right as we are moving from the, metals to non-metals. And it goes down, right, decreasing as we are moving from the top to the bottom down in a column or a group, which is mainly because of the size, right? So the atomic size increases and the electronegativity decreases. Now, we do have some scaling and some values. For example, Linus Pauling is one of them that is helping us to understand, the trend in our electronegativity and the polarity of our bonds based on the thermodynamic, data. But we try to really focus on the periodic table and use the table to predict the relative electronegativity differences between our atoms, if that makes sense. Okay. Okay, now that we understood the electronegativity and how we can use that to understand the polarity of the bonds, we're going to have another look to our nonpolar and polar as well as ionic bonds here. Okay, so for the nonpolar covalent bonds, that will be the case that I have the two atoms that they have equal electronegativity, so they can share the electrons equally. Something like F2 would be a good example for that, right? But if I have a polar covalent bond, the atoms now have different electronegativity, and therefore we're going to have uneven sharing of electrons. For example, for the HF, right, fluorine with more electronegativity pulls the electron density away from hydrogen, and therefore creating partial negative charge on fluorine and partial positive charge on hydrogen, right? So the partial charges are presenting the polarity of the bond between these two. I can also talk about the ionic bond now, which is going to be the cases that the electronegativity difference exceeds 2, which means that I have significant difference in the electronegativity of the two atoms, and we no longer have sharing of the electrons. Now we have transferring of electrons from one to the other one. Lithium fluoride would be a good example. Fluorine pulls the electrons almost completely from lithium, making the bond ionic, right? And generally speaking, keep that in mind, the greater the electronegativity difference, the more polar the bond is going to be, with the electron density shifting toward the more electronegative atom. Okay, excellent. Now, in order to measure the polarity of our molecules, we are going to use dipole moment, okay, which is going to be determining by the products of the charge magnitude and the distance between the charges. So this mu here, right, this is your dipole moment that goes by Q by the R. The expression tells us that the dipole moment is always increasing as the magnitude of the charge increases, and the R, which is the distance between the charge, increases, right? In terms of the unit, it goes by debye, and the equal, like this debye is a unit that equals 3.34 times by 10 to negative 30 coulomb meter. Okay, these constant would be given to you for your calculation. Now, generally speaking, the larger the dipole moment, the more polar the bond is. Okay, and if I have something like a nonpolar molecule, right, let's say you have F2, then we're not going to have any dipole moment. You can say your dipole moment is 0. And that is because the electrons are shared equally, and therefore there is no charge separation, right? And therefore, you can say the dipole moment always quantifies the polarity of the bond, which is helping us to determine if the molecule has a net dipole moment, known as polar molecule, or the dipoles are going to cancel out, and that would give us a non-polar molecule. Okay, they're going to be more about the overall dipoles when we get to our, geometries and structures in our future chapters. That brings us to our practice. So here it says the bond length for HCl is 127 picometer. Calculate the dipole moment in debye, and it says we have the charges of H and chlorine, right? Hydrogen and chlorine, +1 and -1 respectively. Okay, so I'm actually going to write this for you. Bear with me. Okay, so I know that my dipole moment goes by Q, the charge, times by the R, the distance between them. The charges here is going to be our, just the, charge of an electron, the Coulomb charge, which is 1.60 times by 10 to negative 19 Coulomb. And it says the distance is 127 picometer, right? Okay, so I have to convert my picometer to meter. And I know that for 1 picometer, I'm going to have 10 to negative 12 meter. I can cancel out the picometer here. The next is converting your Coulomb meter to debye. And the constant is given. If you remember, it was 3.34 times by 10 to negative 30 Coulomb meter. And that is going to give us 1 debye. I can cancel out the Coulomb with the Coulomb here and the meter with the meter here. My final answer must be in debye, which is 6.08. Okay, cool. Thank you very much for watching this video. If you like it, give it a thumbs up. There are going to be more for you coming up soon. Stay tuned for that. Take care and bye-bye for now.